So, this is J Patterson from Göttingen. We'll talk about ancient history, about Riemann and topology in Göttingen, which is the 19th century. But I actually have known Paddy also in ancient history, not quite 150 years ago, more like 50 years ago in Cambridge. I think we first met
60 years.
Yeah, we met 46 years ago first, so it's a while. But we remained in contact across the oceans and across the sea, and across from number theory to topology, which you can study anyway. Anyway, so we're going to hear about Riemann and topology in Göttingen.
Okay, well, thanks very much, Andrew. Thank you very much for inviting me here. I should perhaps begin by saying one or two things. First of all, I am not a topologist. Somehow I feel myself to be sailing under false pretenses here, speaking to a topology seminar. However, I have lived for an awful long time now in Göttingen, and I've been rather aware of the history of what has happened in Göttingen, and this is the reason that I've got involved in this particular topic. It's also a topic that's closely associated with complex analysis, which is what I suppose I am sort of formally when one begins. This began as an attempt to answer some questions posed by Milner about what Riemann is doing in his paper of 1857. This is a paper called the Theorie der abelschen Funktionen, and it is one of those papers that changed mathematics. It's a phenomenal paper. It's not terribly long. I mean, it's 54 pages long, but everything is given very, very sketchily, and it is a paper that people return to over and over again. Alfors referred to this paper and the predecessor to it, Riemann's thesis of 1851, as cryptic messages to the future. And so the problem is trying to understand these cryptic messages and to understand how he did things. And in particular, this is the first paper in which topological arguments are used in a setting dealing with questions of what were in those days central mathematics. The topology is quite sophisticated. I mean, surprisingly sophisticated, sort of for the time, and for this reason, this opened up entirely new realms in mathematics. It opens up the theory of Riemann surfaces. This is what it's about, and it uses completely new methods. So this is the reason why it's such an important paper to understand. And there is virtually nothing written about topology before this. There are a few questions which have been treated, which you can regard as topology. For example, Euler on the Königsberger bridges, the Euler on the polyhedron formula, Hamilton on the Icosian game, and such like matters. But these were just more like puzzles and sort of small items. Here one gets a really serious mathematics coming in. So it's often referred to before this period as analysis situs, but analysis situs as used by Leibniz refers to something else, and Riemann in fact emphasizes that Leibniz is not thinking of topology in the sense that he is thinking of it. The first person to actually use the word topology was Johann Benedict Listing, who was also in Göttingen, and he plays a very important role here. So let us continue. The history of this whole subject really begins with questions dealing with magnetism. And it is only very appropriate that we're in the James Clerk Maxwell building at the moment. In about sort of 1780 to 1800, the first voltaic cells, batteries, were developed. And in about 1820, Ampere and Ørsted did their experiments on the deflection of compass needles by means of electric currents. And the theory of this was developed in the period following that. In the late 1820s, there were two versions of Stokes' theorem which were proved. Green's formula, which deals with the two-dimensional sort of object with a one-dimensional boundary, and Gauss's formula, which deals with a three-dimensional thing with a two-dimensional boundary. And these were needed in order to formulate the basis of magnetism. I should perhaps say that Stokes' theorem came about 20 years later, and it has a slightly curious history because it was actually not due to Stokes, it was due to William Thomson, the later Lord Kelvin, and it was given as a present to Stokes by Kelvin, both by, I should point out, were Irish, as an examination question in Cambridge. It was so it wasn't actually published as a theorem. It was published as an examination problem. And the fact is that when you look at Stokes' theorem, you see that you have to deal with a boundary operator, and so these are it becomes the analytic basis of homology theories, and you can also regard it as cohomology theories if you so prefer. So this was, I think, first recognized by Gauss, and shortly after this. The date is usually given as 1833. I'm not sure whether this is actually valid. In the 1820s, Gauss had worked on differential geometry, and he had given versions of the Gauss-Bonnet theorem, but I don't think that one can prove these versions without the use of Stokes' theorem. But the next one is Gauss's theorem. So I've written it out in a fairly explicit version here. One has an integral. X, y, and z lie on one curve. X prime, y prime, and z prime lie on another curve in the three-dimensional space. You form this integral, and the assertion is that this integral is 4 pi times the linking number of the two curves. They're closed, simple closed curves, and one gets the linking number as an integral. So this is the first example of integral geometry. It's an integral which represents something very geometric, and in fact, apart from the 4 pi, an integer. And there is a long history of these things. It was taken up to a great extent in the 1940s by Gelfand, and then the apotheosis of the integral geometry is the Atiyah-Singer index theorem. I don't know if this can actually be deduced directly from the Atiyah-Singer index theorem, but it's...
It was certainly aware of Gelfand's work.
Well, Atiyah's and Singer's work was actually a solution of a conjecture of Gelfand's.
Yes, exactly.
Yes, I mean, so there is a long history, but this was the original version. Now, how does this work? What happens is that you take your two integrals, you let us say you fix on one of them, and you show that if you have two homologous curves inside the sort of the exterior of the other curve, then the integrals around these are equal. And that you use sort of slightly with a touch of irony, Green's theorem, not Gauss's theorem. And this allows you essentially to pull one link away from everything else. You can then, so you get something that is just sort of like this. You then move one of the integrals into a straight line by making the circle bigger and bigger. You can then integrate it directly, and it's in any case what is known as Ampere's theorem in electromagnetic theory. So the proof is done like this, and then you reduce it down to, by induction on the linking number. So this is the underlying idea. Gauss at this stage didn't really push it any further, but he, one should say, at this stage he was about 55. He was no longer terribly young, and what he did was to encourage a group of younger people, none of whom were actually mathematicians, to be interested in topology. One of these was Listing, who the other two were Möbius and Wilhelm Weber. So, Möbius was actually employed as an astronomer in Leipzig. Wilhelm Weber came to Göttingen in the early 1830s, worked together with Gauss on methods of actually measuring magnetic fields. Listing was a sort of physicist who, well, he had a sort of complicated life, but he was basically a physicist. What happened was that in 1837, Queen Victoria came to the throne in the United Kingdom. She could not come to the throne in Hanover, in which there was the personnel union so the king of Hanover was a certain Ernst August, who was extremely conservative, and he rescinded the constitution of the Kingdom of Hanover. There was a protest about this. Wilhelm Weber was one of those protesting. Another two were the Grimm brothers of the Grimm's fairy tales. Another one was Evert, who was a son-in-law of Gauss. And they protested, and the result of this was that they got thrown out of their jobs. And in fact, the Grimms got thrown out of Hanover completely in very short time. Listing, in fact, took over Weber's work at this point, and he wrote a book in the 1847, For Studien zur Topologie, in which the word topologie, topology, turns up for the first time. Weber was Riemann's advisor, and he was able to stay on in Göttingen for a few years after the professors were thrown out, and he then became a professor in the early 1840s in Leipzig. Leipzig was where Möbius was, and in fact they had contact with one another. This has been sort of unraveled by Moritz Zepple, who is the person who is the best expert on the early history of topology. And I should say that Listing did all sorts of things. I mean, he is, if you look him up in the various sort of reference books, he is best known for his work on the physiology of the eye. He was also accompanied, what's his name, Sartorius von Waltershausen on volcanology expeditions. He was a physicist and he was a mathematician. His work on mathematics wasn't terribly deep, but nevertheless it was significant. However, there is one thing that is actually quite interesting in this. He was the person who actually first invented the Möbius band, Möbius strip. A year or two before Möbius, actually they may have discussed it together for all I know. The thing is, I suspect if it was called a listing strip now, it would be considered to be something like a Elastoplast or something like that. But the Möbius sounds much more exotic. But this was in the middle 1850s, so about the time that Riemann was writing his paper. Now, it's in this period, 1855 to 1865, that you get the first uses of topology seriously. Riemann's work was very dramatic. This is what I'm going to be talking about. It was in 1857. I just wanted to point out that there is the second piece of work that I know of mathematics, of topology being used in a serious argument outside topology, is the study of the Earth's magnetic field, in which Maxwell unravels. This is in volume 2 of his treatise on electromagnetism. The nature of the southern magnetic pole. There was a lot of discussion about this. It's quite an interesting topic in itself. Gauss probably thought something along these lines, but there is no documentary evidence that I know of showing it. But Maxwell does use his paper on hills and dales in order to do this. So what you find here is, I should perhaps say that in, I think it was 1861, Listing wrote a second book or paper on topology, which then was continued much further by Peter Tate. And Peter Tate, I think, wrote the most extensive obituary notice for Listing. So there was quite a connection with Edinburgh. So this is Listing. Now, those of you who are sort of from this area will sort of appreciate that he looks as if he would have made an excellent Presbyterian minister. Actually, he was quite different. I must say a little bit about him as a person. He came from very poor circumstances in Frankfurt. He got the possibility of studying in Göttingen and moved into the circle around Gauss. He was, amongst other things, an extremely gifted graphic artist. This is a profile, in fact, I think the only profile known of Gauss in his hand. You notice it is done by very simple lines. I mean, this is one sees that he is masterly in this sort of thing. In any case, he, on one time coming up to Göttingen, he passed through Kassel, fell for sort of a girl there, Pauline, got married. The two of them moved to Göttingen, and unfortunately, neither of them was able to handle money. This is where we diverge from the Presbyterian ministers. So they were in continual difficulties and were sometimes on the verge of illegal activities in what he was up to, and sort of helping himself to what we would describe now as deep for mental funds. When he died, his wife, or widow then, reckoned that he was a great man and that he should have a plaque put up. This plaque, since he had the bailiffs at the door, Göttingen sort of objected to this, And there were two things. First of all, there's a plaque on the back door now. I think Andrew has seen
Yes.
it. And there's a rule in Göttingen that no plaque is put up before the wife of the deceased is also has left this earth.
I didn't know that.
So these are I have to explain some things about the geography of Göttingen now. So this is the what's known as the Goethe Allee. It looked rather more magnificent in those days. This was the anatomical theatre. Sort of just behind it is where the station is nowadays. In this house here, I think is where the Grimm brothers lived. And it was the fashionable area in Göttingen. This is a view from the church tower in the middle of Göttingen. So here is the anatomical theatre. You see it's a small town. There is a church here. This is the Paulinerkirche, and it was at that time the university library. This building here contained, amongst other things, Weber's physical cabinet. That's for the Department of Physics, as far as this was concerned. And this building here is where Listing lived. So they were all right beside one another. Riemann lived sort of down here and then round the corner, at least part of the time. So he was always very close to this. All of these are within a very, very short distance. So what you have, oh, I must show you, this is looking at it on ground level again. So this is Listing's house here. It's on the back door compared to this. The front door steps has been moved around the side since then. This is the Paulinerkirche, and this is where Weber worked.
The balustrade is still there.
Still there?
The balustrade.
What?
The balustrade is still there.
Yes, this little house is still there as well. And allegedly Goethe drank tea there on one occasion. So this gives you an idea. Everything was very small, very close. Riemann would have been a student working in here, and he was then a kind of assistant working with Weber in here. So Listing and Weber and Riemann were all together. And I think this is extremely important to realise. The previous picture is actually 1850. So you can imagine Riemann sitting in here brooding over complex analysis. Is entirely contemporary, as it happens.
Where did Gauss live?
What?
Where did
That's the next picture. I think it's
I see,
the next
okay.
picture. No, it's the picture after the next. This is another one of the same area again. And then we get to Gauss. So Gauss lived in this Olympian, this was the observatory. This is the defensive wall around Göttingen. And this Gauss lived out here, in this side here, in this part of the building. This, I think, was a magnetic observatory. And he lived really, by this time he was into his 70s, so whenever Riemann was around. So he was in ill health, and he was the sort of person who was not very approachable, and being outside everything, he was there. However, Andrew showed me a paper by André Wey, which contains a letter of Betty, Enrico Betti, which he Betty recounts that Riemann had actually spoken to Gauss had spoken with Riemann and described something. So this is a typical student sort of study at the time. So this gives some idea of what Riemann would have been living in. Okay, good. Now we come to the mathematics. What is happening now is that the Gauss Listing had certainly been thinking about topology by 1850. Weber had been in touch with Möbius and had brought some of these ideas back to Göttingen. This is something that Maurice Epley has worked out. And Riemann has had the idea of how to define connectivity of various regions. So these are from his 1857 paper. So I should say next that he had already proved a very important theorem in his thesis of 1851. This is the so-called Riemann mapping theorem in one version, which says that a simply connected region is which is not compact. If it's compact, it's the Riemann sphere. If it's not compact, it's either the plane or it's holomorphically equivalent to a disk. And this is proved using the Dirichlet principle. And if this is something else that I should point out here, the ideas that Riemann used actually can be found in a paper of 1847 of William Thomson again. Thomson only goes into this once. It's a short paper. He doesn't go into the consequences of it. Dirichlet used the same idea in his lectures. I don't know if there's notes of the lecture course of 1848. Or I should say that Riemann spent 1847 to 1849 in Berlin, where he met Dirichlet and he met Jacobi. And my impression is, and this is something that I hadn't realized before, that Riemann learned a great deal from his personal contacts and from the lectures of other people. In fact, in Germany, it is much more common, or is much more traditional, that lectures are a way of transferring information. So in any case, the idea is that if you have a simply connected region, you can put a logarithmic potential onto it. You can then solve the boundary value problem, as said by the Dirichlet principle. You can solve it by other methods, and then by considering the conjugate function, you get a map from that region into as long as the boundary is non-trivial, into the disk. So Riemann by 1851 knows what a simply connected region is, and he starts defining sort of a multiply connected region by sort of what he calls Querschnitte. You make a cut, and then what's left is sort of a simply connected region. So this is two-fold connected. I mean, so in Riemann's terminology, simply connected is what we call simply connected. Twice connected is when we make one cut and we get a simply connected region, and a region that we then, because of the theorem, we actually understand. And then he goes on to threefold, what he calls threefold connected regions. So here you have two Querschnitte, two cuts like this, and so this is okay. And then he gives this example, and this example perplexed me for a long, long time. So he gives this thing, which is clearly a sort of Riemann surface, but it goes over itself, sort of like sort of one bit goes over the top, the other bit goes under the bottom, and then we have the cuts here and here. Now, this is the bit that requires actually, is what requires some meditation. What happens is, in the case of, what Riemann is trying to do is to analyze algebraic functions, that is, functions which satisfy some equation like this. And he will project this onto the x-plane, which is a complex plane in his case. And there's a map that's from the curve defined by this, and we will assume it's irreducible and so forth. And there will be points of ramification. And the points of ramification were analyzed in 1850 by a student of Cauchy's called Puiseux. And Riemann uses Puiseux's theorem without ever referring to it. This is one of the things that is very sketchy in his paper. But what this means is that you can essentially uniformize around a ramification point using something like a function like x minus x naught to the 1 over n, something like that. This means that you can, what it means is that you can cut out around each ramification point a circle, you look at the covering map, and it's exactly something like this. So what Riemann is doing at this point is he has taken the Riemann surface, he's cut out around each ramification point a circle, and then he gets a situation like this. And this, so I've said. And so what he does is he gets this region like this, and he then sort of argues with these other things that are going sort of orthogonally to the Querschnitte, that the homology of the whole region is z to the q for some q, and if you include the sort of look at the relative homology, what you're getting are sort of z to the 2q with the two lots of things with a sort of intersection matrix, which is given by this. So these are just exactly what he has drawn pictures of. So what Riemann is not doing is classifying the two-dimensional surfaces. This was done a few years later in a paper which was published by Möbius. Möbius was at this time over 70, and one can assume that it was probably written much earlier, but that he saw no point in publishing it. So, and then what Riemann does so what we've got is not the Riemann surface, but we've got the relative cohomology of a Riemann surface with holes in it, with circular holes in it. And then he argues that the homology is z to the 2p. He doesn't say it like this, but this is what it comes down to, for a suitable p with very similar intersection matrix. Now, the question is, what is this P? He identifies it with the differentials of the first kind. Now, this is Abel's definition of Abel doesn't call it the genus of a curve, but it's a sort of parameter introduced by Abel. Abel wrote an absolutely brilliant paper. It's as brilliant as Riemann's, but it's algebra, and it's just out of this world. And it was written in 1826. Cauchy did not understand it, and it only got published in 1841, I think it was. And the result of this was that others sort of had a much less sophisticated approach to the whole business, especially Jacobi. However, what is rather odd is that if you study Riemann's papers, there is no sign that Riemann had read a word of Abel. And he doesn't seem to have read. He seems to have learned what he needed to know from his connections with Jacobi. Maybe, with Jacobi. I think there's probably nobody else that he could have done this from. So this is the argument. Now, what Riemann does not do, that particular point is. It turns out that what he needs for the argument that he is going to carry out next is exactly the intersection matrix of the homology group. One might have thought that he would have had some, using the ramification, one can describe the genus in terms of this is the Riemann-Hurwitz formula. One might have thought that in a slightly sort of contorted version, and one might have thought that he would have tried to do some type of combinatorial topology, he does not. He sticks to this very simple and straightforward argument and gets away with it. I mean, the thing is that this is I think one of the points where you actually see his genius. Later, Möbius and Jordan sort of classified compact surfaces so that this was done. Now, the thing that confused me when thinking about Milner's question was that I have read a great deal of Klein, and Klein does not use this kind of excision argument. He studies very precisely the behavior around the ramification points and has very sort of specific drawings showing how this works. And from what I can make out in both Karl Neumann and Hermann Amanda Schwarz do this as well. So
maybe you should state Milner's question.
Sorry?
Maybe you should state Milner's question.
Well, Milner's question is actually at the beginning of the whole business. How did Riemann think about topology? So this is, I've answered it in this sense. And the next question is, where does the word genus and the German word Geschlecht come from? It seems to be first used, not quite in the present sense, but almost by Klepsch, sort of a few years later. I'm not sure that that's all that helpful, but the concept comes from Abel,
how did Riemann identify P with the number of differentials of the first kind?
By means of using the Dirichlet principle again. So he actually creates functions. So the way that one would do it nowadays is quite astonishing, because one would think that this is not possible, but somehow he does it. And I will admit that I have not understood up to the present everything that Riemann has done. But he gives an argument in order to identify this, and it is he is making use again of his thesis. So it is at high level. It's not whereas, but he does come. He does use a sort of rather explicit formulae for it, but as far as I can make out, and I have to be a bit reserved about this, the argument is an analytic one, and he not only needs the existence of the differentials, but he needs that they are on one sort of part of the one Lagrangian subspace of the homology, that they all have periods 1. And what he is going to do, as soon as he has done this, is to prove the Riemann relations for the period matrix, which is what his real goal is. And everything leading up to this is, in fact, rather brief. You're left guessing at quite a number of points. But as I understand it, this is how it goes. What I would also like to say is that Riemann's work was recognized very quickly. There are some people who have written that it was not recognized at all in his lifetime. This is nonsense. I mean, it was people like Neumann and Karl Neumann and Hermann Amanda Schwarz were actually giving rigorous versions of what Riemann was doing, even while Riemann was still alive, in the early 1860s. Weierstrass had developed his own theory of abelian functions. He had a good relationship with Riemann. I mean, despite having very different philosophy of mathematics, he was the person who was responsible for having Riemann elected as a corresponding member of the Berlin Academy. And Riemann's paper on the Riemann zeta function was a thank you for that particular thing. So it was, Weierstrass's arguments are much more sort of what one would describe nowadays as sheaf theoretic. So these arguments are were brought together in Weil's book. I perhaps should mention here, I haven't put it on these things, but there is a nice story that Remmert from Münster has sort of unravelled that Klein was struggling with, this was in about 1870, was struggling with Riemann's idea of a Riemann surface, and he writes in his little book on Riemann's theory of algebraic functions that he thanks sort of Prim for the sort of the insight that Riemann was really thinking of very abstract surfaces when he was doing this. And Remmert found a letter, I think, of Prim's, in which he says that Prim himself didn't say anything like this to Klein, and he himself had never even thought it. So the idea of a manifold, which was then taken up by Hermann Weyl, seems to have developed sort of out of nowhere in a sort of an imaginary conversation. So the next point in Riemann's paper, and this is actually what he is aiming for, is that he uses Stokes, the Cauchy theorem or Stokes formula to prove the basic properties of the period matrix. This is and then from that he develops. This was sort of coming up. This was the way that Riemann does it is pretty well the way that one does it nowadays. I mean, and he develops then the theory of theta functions, which you can regard in several different ways. And I wanted to make this point here, since we're in Edinburgh, that so the method that Riemann uses was taken up by Sir William Hodge in his harmonic integral. I should perhaps also say that the first chapter in, well, there's one or two things. Maxwell is the first person to really distinguish between vectors and covectors, and this is in the preliminary chapter in his treatise, and he is therefore thinking in a sense at the analytic level of homology and cohomology, and these sort of different B's and H's and E's and D's that he introduces for the magnetic and electric fields are a result of this. And Hodge refers to the Maxwell equations in the first chapter of his book. I mean, this is where he sees his motivation. So there is a connection. It was also sort of thinking when I was coming here this afternoon that I met Sir William Hodge once in my life, so I was introduced to him, and I was thinking that at that time, I was about as old as Riemann must have been, and Hodge was about as old as Gauss must have been. Gauss must have been pretty intimidating for Riemann at that time. And, this was I met him when there was a conference for his 70th birthday in 1973. In Riemann's paper in his Habilitation, he gives an awful lot of detail, bibliographic detail, about the theory of trigonometric series. And I had assumed from that he read a great deal in the Pauliner Kirche, sort of where I showed you. But in fact, if you read a little more carefully, he actually thanks Dirichlet for giving him this information, and he seems to have just copied out what Dirichlet told him. He seems to have learned a great deal from the people that he studied with. That was the group in Göttingen, Weber, Listing, and then at one remove Möbius, and then in a sort of a kind of exotic way Gauss. And when he was in Berlin for 2 years, he learned from Jacobi about the work of Rosenhain and Goepel, which made an attempt to develop a theory of theta series for genus 2. This is actually it's actually very interesting to read, but it's using a crutch to get started. I mean, it uses the fact that one's dealing with hyperelliptic curves. I don't think you want to know over much about this, but the the theta functions can be regarded as sections of a line bundle over the Jacobian. And so what this means is that you can actually develop a theory of functions on the on an algebraic curve using theta functions, and it's analogous to Jacobi's use of theta functions for developing the theory of elliptic functions, the theory that is described in the Fundamenta Nova. In the general case, it's much more subtle because you're dealing with a p-dimensional manifold, and it's the Jacobian manifold, and it turns out to be very, very important later on. There was more or less as a response to what was going on, an algebraic theory developed. This was by Klepsch. This was about 1870. By Gordon and by Max Noether, and by about 1880, Dedekind and Weber on one hand and Kronecker on the other hand had developed essentially a theory of algebraic curves, which is so algebraic that you didn't really need an algebraically closed ground field. It was not. Unfortunately, it took then. The next developments took 45 years after that, and they were done by Arkin.
When was the Jacobi part of Abel-Jacobi proven?
What?
The Abel-Jacobi theorem. When was that?
It depends what you mean by the Abel-Jacobi theorem. Abel's part of it was proved in this paper of 1826, but it doesn't say what one thinks it says nowadays, because he was thinking in algebraic terms, and so it's given in a rather different language. Jacobi gives a sort of version of something close to the surjectiveness in papers of the 1830s, but it took a long time. It was really, I think, in the work of Solomon Lefschetz that the theory of the Jacobian really takes on a fairly solid form. And reading these things is hard work. I mean, because what happens is that the language is often inadequate. And what you find is that the language improves step by step. Later on, André Weil uses the theory of Jacobians for his the Mordell-Weil theorem, and in that he has to use the theory of theta functions as a crutch in order to prove all the bits and pieces that he needs about Jacobian. And it's only in the 1940s that you have a proper theory of Jacobians. And so the whole thing is a very long, slow process occurring. So you see bits and pieces of it appearing, but it's never quite what you think it ought to be. So, but there are it's about 1837. There's a paper of Jacobi's, and 1826 is one of others. But it doesn't look like what you think it should look like. And there was a sort of another analytic method of developing function theory on curves, which was using the theory of automorphic functions, which was developed by Schwartz, Klein, and Poincaré. I should say that Klein was the person who really developed Riemann's ideas most. I mean, it's extremely interesting to read what he has to write. Andrew has warned me. I need about another 5 to 10 minutes, sort of as warning. So they.
I thought it would be much more. I said it's going to be more than 5 or 10 minutes at this point. You should give people a chance.
No, I think I can do it. Yeah, the 5 to 10 minutes, because most of what I have to say are general remarks about the developments after this. Why were people studying topology in the early days? What you see in Riemann's work is that he was studying the theory of algebraic curves. The other direction, which was a major stimulus for topology in the early days, was the theory of differential equations. So this was especially in the hands of Poincaré and of Lefschetz. When you're reading this, one of the things that is really terrible about it is that there are no such things as homology groups and so forth. It is, there are all sorts of numerical invariants which require a lot of effort to understand. But Riemann was interested in differential equations, and you can regard the theory of elliptic functions as a theory of differential equations. But the idea of studying the topology of a flow only appears in about 1890 in the work of Poincaré, and was really taken up by Lefschetz following that. Riemann, one of the motivations for the theory of Riemann surfaces was the theory of the hypergeometric equation. In my original plan for this, I was going to speak about that at some length, and then decided that I probably better not. However, being in Edinburgh, I should say that if you really want to know about this, you pick out your copy of Whittaker and Watson and read the relevant chapter. It is an excellent account. Yes. Yes, what I also wanted to point out that Riemann worked on nonlinear equations, he worked on Bessel functions, but he showed no interest, one of the few people as far of this period who showed no interest in celestial mechanics, Hamiltonian mechanics, or anything like that. It is slightly odd that this is the case. But he died so young that it's perhaps not altogether surprising. One of the things that followed, and followed very rapidly, Riemann's work was a study of algebraic varieties of higher dimension, and especially surfaces. So there were Kummer surfaces, which were studied by Kummer. There were cubic surfaces which were studied by people like Cayley and Salmon in Dublin. There were cubic surfaces is also studied by Clebsch. The Clebsch diagonal surface is this most famous one. And so what people were trying to do, you get some formula for a surface, and the problem is how do you find out what it looks like? And there was some very ingenious work done, on the one hand by Kummer about his surfaces, and on the other hand by Klein and by various co-authors of Klein about cubic surfaces. There's the very famous sequence of Rome surfaces, the ones in the plaster models, are a result of exactly this investigation. And Klein unravels this in great detail. Klein never shows any particular interest in homology theory, and in fact homology and cohomology are, from one point of view, very weak invariants of the shape of an algebraic object. But they are connected with the differentials, and the differentials on algebraic surfaces and so forth were the study of a lot of people in the later 19th century, especially the Italian and French schools. What they did was to get this identification between the differentials. What happens is that the whole thing turns out to be much more complicated than it is in the case of curves, where the number of differentials is the genus. and there were all sorts of results proved. All I know is that it is extremely complicated. If you want to find out about this, you have to find a sort of an algebraic geometer who can speak in sort of reasonably coherent sentences. This is not altogether easy. The whole problem took an awful long time to resolve, and again, it is exactly the work of Sir William Hodge in 1937, 1941. It did this.
He was born half a mile away from here.
Yes, yes. That was, and one should also add, he was of course the teacher of Sir Michael Atiyah.
Of course.
So this was the closure of that particular period. One last thing I should say is that about 1930, Emmy Noether unraveled the whole work that people like Poincaré and Lefschetz had been doing, and defined the notion of a homology group and of a cohomology group. Although there are those who argue whether it was she that was the first one, but the authorities like Hertzebruch believe that Emmy Noether,
Yes.
believe that Emmy Noether was the the originator of this, and it's one of the few examples of somebody who has revolutionized a subject with 0 papers in it.
Yes.
So she never wrote anything about it whatsoever. And but at this point, one moves. At the time of Riemann and Maxwell, you were dealing with topological arguments in mathematics. By 1930, there is real topology existing, and topology has become a subject in itself. I think one can say there are topologists, there are people who describe themselves as topologists, and that is then the end of that particular era. Okay, so I'll stop at this point.
Thank you very much. Are there any questions? Who would write all this?
What?
Will you write a book on this?
The person who's supposed to write all of this is Maurice Etlev. He is the person who makes a living out of it. I'm in the position now of being retired, so I don't have
But you have more time.
pistols at my ear, sort of, or my temple, sort of a people. The thing, there are quite a number of areas of mathematics, and topology is one of them, where there are large blocks of history that are not properly covered by good accounts. And this business of the origin of what happened in the 1850s is one of these. I mean, it's not just here, but you're quite right. There is a real need for somebody to do this, but it is very hard work.
Yes. Thank you very much for doing that much at least.
Okay.
Thank you.